Hello students, welcome to the next module in which we'll be deriving expression for mechanical force per unit area for the charged conductor, right? So let us our module. Now students, let us consider a positively charged conductor of any shape, right? So let's say here I'm having a conductor which is irregular in shape, and this particular conductor is positively charged, and this conductor is placed in a dielectric medium having dielectric constant K. Now students, see the shape. Is it regular or irregular? It is irregular. So distribution of charge will be uniform or non-uniform? It will be non-uniform. And as distribution of charge is non-uniform, I can say surface charge density, that is sigma, it is nothing but equal to charge dq upon area ds, right? So therefore I can write sigma, it is equal to dq upon ds, right? Now let us move further. Let us take this equation ahead. Right? Now students, as we want to find mechanical force per unit area, we'll consider small infinitesimal area on the surface of the charged conductor. Now see the diagram carefully. There we are considering small infinitesimal area ds, right? Now for this we'll consider 2 points. First of all, we'll consider point A, which is just outside. Now see diagram, see point A, it is just outside and it is very near to the surface of the charged conductor. And the similar way, the way we have considered point A, in the similar fashion, we'll consider another point B, which is just inside. Now see the diagram again. Point B, it is just inside and it is very near to the surface of charged conductor, right? So we have considered 2 points, point A, which is just outside, and point B, which is just inside, right? Now students, let us consider now this elemental area ds will have some amount of charge, right? And that will be elemental charge, and that will produce intensity at point A as well as at point B. So let E1 be the electric field intensity which is produced by the elemental charge, or rather by small charge which is present on small area ds. Now students, the way smaller charge has produced intensity, in the similar way charge on the remaining area will also produce intensity. So let E2 be the electric field intensity which is produced by the charge on the remaining area of the conductor, right? So E1 is the intensity due to small charge, E2 is the intensity due to charge on remaining area, right? Now let us move further. Now students, this particular situation we have already analyzed, right? For point A, we know that both the intensities are in the same direction. So see diagram, E1 and E2 are in the same direction, right? Now as E1 and E2 are in the same direction, resultant intensity at point A, it is equal to E1 plus E2. Why it is equal to E1 plus E2? Because both the intensities are in the same direction, right? Now student, point A is just outside, and for point which is just outside the charge body, intensity is given by EA, it is equal to sigma upon epsilon, right? Now let us move further. Now see these two equations, left hand sides are equal. So from these two equations I can write E1 plus E2, it is equal to sigma upon epsilon, and let this be my equation number 1, right? Now let us move further. The way we have dealt with point A, we'll consider point B now. Now see point B, it is just inside, and we know for point B both the intensities are in opposite direction. Now see the diagram, E1 and E2 are in opposite direction, right? So therefore resultant intensity at point B can be written as mod of E1 minus E2. Why? Because both of them are in opposite direction. And again, as point B is inside the charge conductor, intensity at point B should be equal to 0, right? So I can say EB, it is equal to 0. So I'll be putting the value of EB in this particular equation. So what will I get? I'll get 0, it is equal to mod of E1 minus E2, or mod of E1 minus E2, it is equal to 0. Now from this, I'll get the final answer as E1, it is equal to E2, which will be my equation number 2, right? Now let us take it further. Now let's see equation number 1 and equation number 2, right? Now what will I do? I'll replace E1 in equation number 1 by E2. Why? Because both of them are equal. So what will I get? I'll get E2 plus E2, it is equal to sigma upon epsilon. So this will become twice E2, it is equal to sigma upon epsilon. I'll transfer 2, so what will I get? I'll get E2, it is equal to sigma upon 2 epsilon, right? And this is nothing but intensity which is produced by the charge on the remaining area of the conductor, right? So from here I can write E2, which is also equal to E1, it is equal to sigma upon 2 epsilon, right? Now students, see this elemental area ds, right? I can say there will be charge element, right? Elemental charge on this, and this elemental charge is present in electric field intensity E2, which is produced by the charge on the remaining area of the conductor. And this remaining charge, or rather charge on the remaining area, will try to push this particular element in the outward direction, or I can say this element will experience the outward push. See the diagram carefully. Here it will experience the outward push, right? Because of the charges on the remaining area of conductor. right? And this force will be perpendicular to the surface and it will be directed outward, right? So let us move further and we'll be calculating this particular force. So I can say mechanical force which is acting on elemental charge, it is nothing but equal to elemental charge on ds, and this charge ds has to be multiplied by electric field intensity due to the charge on the remaining area of the conductor. Why? Because it is placed in the intensity of remaining charge, right? Now let us move further. So therefore I can write mechanical force F, it is equal to dq multiplied by E2. Now from formula of sigma I can find out the value of TQ. So what will I get? F is equal to sigma ds, and the sigma ds has to be multiplied by E2, right? What is E2? It is sigma upon 2 epsilon, right? Now I'll transfer ds, so I'll get small f which is equal to capital F upon ds. It is equal to sigma square upon 2 epsilon, and this is nothing but the expression for mechanical force per unit area which is acting on the charge conductor, right? Now students, see 2 epsilon, it is again constant in this case, and as 2 epsilon is constant, I can say this mechanical force per unit area is directly proportional to sigma square, right? So students, in this particular module we have learned a very important derivation of mechanical force per unit area. So that's it for this particular module. I'll see you in the next module.